For this video, I decided to build a time-lapse camera using pulse width modulation.
And to do that, we're going to use a normal digital camera that doesn't have a time-lapse feature on it, but we're going to add that feature by controlling a servo to press the shutter and the power button for us.
For the camera, I chose the Panasonic Lumix. Not only is it small and cheap, but it takes good pictures and is waterproof. Next thing we're going to need is servos. So luckily, I was able to figure out a way to crash my plane, and I salvaged the servos from it. After sourcing the servo, I then drew up a mount to put around the camera. Bam! So I used plexiglass for this project because it's pretty easy to cut and it's really easy to bend with a little bit of heat. And it has the strong potential to look good if you know what you're doing. The first version of this mount did not work so well. Every time the servo would press on the button, the plexiglass would just bend and move out of the way. So now the fun part, how do we make the servo move? Servos are an easy way to add controlled movement to your project. And there's not much to them either, just a controller, motor, and a couple of gears to help with torque. Luckily, most servo communications are the same. The PWM period must be 20 milliseconds, and the arm movement varies from 1 millisecond to 2 millisecond pulse width. A pulse width modulation signal is defined by its frequency and its duty cycle. Here we are looking at a 50% duty cycle, where the signal is only on 50% of the time. What's cool about this is the measured output voltage will also be 50%. For example, if your peak voltage was 5 volts, the output would be 2.5. Here's what 25% duty cycle will look like. 25% of the time the signal is high, 75% of the time the signal is low. But you may be asking yourself, what is time? Time is the period of the signal. Here you can see where the 50% duty cycle repeats itself, creating the frequency. The frequency is pretty easy to calculate. It's just 1 divided by the period. Because we know our period must be 20 milliseconds or 0.02 seconds, we can see that our frequency will be 50 Hertz. This means the signal will repeat itself 50 times per second. Because we know our pulse width and our period, we can calculate our duty cycle. Because our pulse width is 2 milliseconds and the period of the signal is 20 milliseconds, we can see that we will have a 10% duty cycle.
So next thing we need to do is get some hardware to generate the PWM signal for us so we can start moving this servo.
The hardware that I will be using to create this PWM signal is an inexpensive prototyping kit developed by Cypress. For any PWM module and a microcontroller, you will have to assign it a clock signal. To make the pulse width calculations easy, I created a clock signal of 1 megahertz. Because our clock is running at 1 million hertz, or 1 microsecond, we have to count to 20,000 to reach our 20 millisecond period. We also set a capture compare value at 1500. This will be the point in the signal where it changes from high to low. This is just a default for now, and we will be changing this value to move the servo.
Great, so we have the hardware ready. Now all we need to do is control the hardware with some software.
So here is our software design. We are going to use a simple state machine. When the software starts, we want it to power on the camera, focus the image, take a picture, and then wait, and repeat this forever, or at least until the batteries die. Through experimentation, I found these pulse width values for each action. A good tip if you're using state machines is to enumerate each state. This will allow you to define the states by words instead of just numbers. Here is our state machine in code. As you can see, this section of the code will just run forever. It's always a good idea to let your user know that the device is running, so if you can, flash an LED or something like we do here. Usually, state machines are nothing more than a switch statement. Here you can see we start our state machine with the power on, take the picture, power off, and then wait the amount of time that we want before we power on or take the picture again. I have them in order here, but each state just links to the next and then continues forever. One cool thing I want to show you here is how to slow down your servo. I didn't want the servo to slam the buttons on the camera. So every 20 milliseconds, I slowly increment or decrement the position. This will allow your servo to have nice smooth movements using interrupts. Here's the picture taking loop working. First it starts in idle, then goes to focus, takes the picture, and returns to idle. Alright, so we are controlling the PWM pretty good right now, but we need to put this in a project box because there's no way this will survive outside. I first started by mounting the PCB board, then cutting away sections for the 9-volt battery and our two-way switch. Since our microcontroller only uses 5 volts, I installed a voltage regulator to convert the 9-volt battery to 5 volts. Next, I soldered in our microcontroller, switch, and servo wires. Well, here it is, the finished working project. You can see as soon as I turn it on, the camera will power on, get focused on the image, and then take a picture of the elusive stone blue jay. At the beginning of this video, you saw some time-lapse videos that I took with this camera. It usually takes about 500 pictures before the batteries die on it. Well, I hope you enjoyed this project. I thought it was really cool, and now I have a really nice tool that I can use outside to get time-lapse videos. And speaking of time-lapse videos, I have one more to show you at the end. So thanks for watching, and remember, code will make it go.